Hi, we're a two-person team, Colin McCarthy and Tristan Grubb. We have developed a flood model for cities and regions. Knowledge of how and where water moves across a landscape is necessary for resource managers and local planning organizations. Modeling is key to predict where flooding may occur. Flooding can adversely affect health and water quality. It also causes property damage. Models can help planners, environmental scientists, and community members fortify infrastructure in high-risk flooded areas, predict nutrient and pollutant levels in streams, reduce fluctuation in various water bodies, and improve stormwater infrastructure. We use our models to predict flood inundation in Calgary. We use Minneapolis to validate the generalizability of our model. We divide each city into grid cells and classify each city's grid cells as inundated or not inundated, based on past events, or DEM flood inundation models. We use features to predict inundation. Features such as land use type, demographic data, tree canopy, soil type, and distance to water bodies. Our model identifies the common characteristics associated with inundated or not inundated areas. We then split our data into a training set and a test set. The training set identifies the common characteristics of the data, and the test set predicts whether a grid cell will be inundated or not inundated based on the training set characteristic. We can evaluate the effectiveness of our model by how many grid cells the training set predicts correctly. Distance to water is a highly significant feature. For each of our features, we compare inundated cells to non-inundated cells to find significance. This shows that the farther a grid cell is from a water body, the safer the grid cell is from flooding. A count of buildings within each grid cell is another significant feature in both cities. There are fewer buildings in inundated cells. Property values are much lower in inundated areas. Open space tends to be more inundated than space occupied by buildings, infrastructure, or other features. This is interesting. The cities are both significant for tree canopy, but differ on this significance. Minneapolis has more tree canopy across the city that can mitigate flooding. Calgary is more arid. Trees tend to locate near water bodies where flooding is more likely. This feature is still included because it is significant in both cities. Riparian soils tend to be more flooded than non-riparian soils. Our model is broken into training and test sets. We then predict on the test set. All of our features are used to create the model. The confusion matrix helps us understand the model's performance. Is it better at reducing false positives or reducing false negatives? We want a model with low false negatives because the costs of flooding are high. Our Minneapolis model is much better at identifying correctly flooded areas. Its sensitivity, 0.85, is much higher than Calgary's, 0.35. This map shows the model results in colors. The gray grids are our training grids. This map helps us see where false positives and false negatives occur. This is the final product for the client, showing predicted probabilities of flooding for each grid cell. This map shows cells with above 20% predicted probability of flooding that do not contain water, in orange. These are predicted inundated land cells. The goal of this exercise was to identify high-risk areas for flooding using features that could model this risk. We tested many features and distilled those down to a few that displayed a significant difference between inundated and non-inundated areas. We only used features present in both of our cities of interest, Calgary and the validation city, Minneapolis. These features were average distance of a grid cell to a nearby water feature, the percent of the grid cell that was impervious, the building count within the grid cell, the average assessed value of properties within the grid cell, the percent open space, the percentage of tree canopy, and the percent of riparian soils. The distance to river or water body was highly related to whether or not a grid cell was inundated. It was by far our most significant feature. This makes sense. Water bodies, especially rivers, would be a major source of floodwater. The percent of impervious surface was significant for both cities and especially for Minneapolis. Minneapolis has a more developed area than Calgary. Calgary has more soil coverage and less overall development density. Therefore, flooding from impervious surface runoff would be more significant in Minneapolis than in Calgary. The count of buildings was another significant feature. Comparing inundated and not inundated areas, it was clear that people tend not to locate near inundated areas. This makes sense. It is not desirable to build a home in an area that is likely to flood. Areas near water bodies can often have steep slopes that make construction difficult, further decreasing the desirability of building near water. This feature was more significant in Minneapolis than in Calgary. This could be the result of Minneapolis's inundation extent. It includes less non-water body land. With a greater proportion of overall inundated area being water in Minneapolis, we would expect fewer buildings than in Calgary, which has a larger area of non-water inundated land. Regulation also discourages floodplain construction, leading to lower building counts within inundated areas. FEMA flood maps discourage construction. Local governments discourage building within FEMA flood zones. Insurance rates are also higher within floodplains. This logic applies to another one of our features, assessed home value. Home values were lower within inundated areas. People do not want to place expensive construction in a floodplain. Industrial uses and nuisances such as noisy highways also often locate near rivers. This would decrease home value along rivers. Decreased home value might therefore slightly correlate with water body distance, our most significant variable, if undesirable activities locate along rivers. Our ROC curves show where our models have good predictive value. Both curves were far from the 45-degree diagonal of the ROC space. Minneapolis outperformed Calgary. This was to be expected. For many of the features, Minneapolis had a greater difference between inundated and non-inundated grids. The specificity of Calgary's confusion matrix results were only slightly higher than Minneapolis's. Minneapolis's sensitivity was also higher, 0.85 compared to 0.35 for Calgary. The specificity and sensitivity of the models is important to discuss here. Sensitivity is the ability of a model to correctly identify grid cells that will flood. Specificity represents the model's performance to correctly identify grid cells without flooding. Because the costs of flooding are high, we are more interested in a model with greater sensitivity than specificity. Identifying a few grid cells as inundated that turn out not to be is far less costly than failing to identify flooded cells. While lower sensitivity of Calgary's model is of concern, this model should be improved in the future to reduce the number of false negatives, or the number of grid cells that were identified as not flooded but turned out to be previously inundated. We encourage cities to develop flood models such as our own, to plan for increasingly hard to manage climate change impacts. Early intervention will save lives and prepare cities for a changing world. Thank you for watching our presentation.